So first off, Mark is an associate professor of statistical methods in the Department of Psychology at Nottingham Trent University. So Mark, I'm going to hand over to you.
Okay. Okay. So let me try to move that. Okay, is that visible?
Yep, that's great.
Okay, great. So let me just get straight into it then. So if we look at the number of publications in across the sciences that use the term Bayesian in their abstract or title or keywords, we see a common pattern across multiple different fields. So in this plot here in the upper left, we have got all the fields, and then we have got various different fields: biology, that's agricultural and biological sciences; business and management; computer science, that's also including things like machine learning, artificial intelligence, and so on. And then the rest are hopefully pretty explanatory. And you see a common pattern. Basically, in the last 25 years, last 2 decades, 25 years, there's been this sharp increase in the number of publications on the topic of Bayesian methods, Bayesian data analysis. Some fields have maybe kind of started that. The statistics, for example, kind of got off the ground maybe a bit earlier than other fields, maybe in the 90s. And then if you look at, for example, psychology there, no movement in the 90s really, and it kind of started in the noughties and really in the last 10 or 15 years. So now, one problem with this is that this is just the total number of publications that are on the topic of Bayesian methods, and it could be the case that across across sciences, there's just been a proliferation of journals and articles on everything. So if we were to plot the distribution of any topic at all, it could look like this. So any topic in science at all could look like just this steep increase. So in this second plot here, what I'm looking at is the proportion of the publications each year in some selected journals that are on Bayesian methods. Now, obviously, there are hundreds or thousands of possible journals I could look at. I just wanted a small number of journals that are on statistical methods. And so I've got, like, for example, the Journal of American Statistical Association, Statistical Science, the Journal of the Royal Statistical Society, and then some in the field of psychology, just because I'm more familiar with those, and then some in medicine as well. So all of these are statistics journals and, on statistical methodology in general, or for some specific fields. Now, what we see here is a kind of a common pattern as well, that like there's just this increase from very low proportion of Bayesian methods, and like in the 90s, up to the 90s or so, and then there's this increase, and it kind of going up to around 20%. So around 20% in most cases. So obviously it's not identical in all those, and like we statistical science, there's something going on. It's kind of dipping down. Who knows what that is? But there is this. It isn't just that first plot wasn't just an illusion. There is just a higher proportion of journal articles covering Bayesian methods. Okay, so why? One question is, and I just want to deal with this very briefly. Why has this happened? Why are we using Bayesian methods now when we weren't, 50 years ago? And I think the answer to that really is computational power, and to kind of just to clarify that or explain that, I would say that for any statistical model, if you can evaluate this function here, and I just, in the interest of time, I won't go into detail, but if you're familiar with Bayesian methods, you know what I'm talking about. This is the likelihood function, which is just a function over the parameter space of the model, and the prior, which is probability distribution over that parameter space. If you can just evaluate those two functions at any point in parameter space, then you can evaluate their product, and that's sufficient then to sample from the posterior distribution using Markov chain Monte Carlo methods, which Ben is going to talk about in more detail. And then that is going to give us this probability distribution over basically all the unknowns in the model, conditioned on what we know or assume in the model. And increasing computer power in the last many decades has just made the cost of using Bayesian methods and using Monte Carlo, Markov chain Monte Carlo methods, just increasingly low. So the cost in terms of the hardware is just exponentially decreasing, and cost also in terms of time and effort. So a few decades back, you could do Bayesian methods, MCMC Bayesian methods, but there was a lot of work involved. You know, you'd have to do a lot of relatively low level programming. Now, using high level tools, probabilistic programming languages like Stan and so on, it's just become so much easier. So this, I think, is the reason why Bayesian methods are proliferating. Now, compare the practice in statistics and data analysis generally, statistical data analysis generally across research as science, with the teaching curriculum. Now, I must apologize for this. It's a gross simplification, but I'm trying to just get at what I think is, I hope is, the kind of the core of the statistical topics that are widely taught, not in, you know, statistics departments, which will cover a very wide range of topics, but just kind of in the sciences. So I'm thinking this is quite typical in a psychology degree, and I think that that's relatively typical in many other fields as well. Right. So basically, it's you know, introducing, you start with covering descriptive statistics, exploratory statistics, and then you start getting into inferential statistics, and you talk about populations and samples and sampling distributions, and maybe talk a bit about normal distributions, and then you're on to the good stuff, you know, p-values and confidence intervals and hypothesis testings and so forth. And then, having kind of covered all of that general inferential statistics stuff, you explore that usually mostly through kind of regression models, linear regression models, and then ANOVA, which of course are just linear models as well. So, you know, various different types of these linear models then. So I think that this is sort of the core, and it's a very rough representation. I apologize, but I think it's the core of what of statistics as it's taught across many different fields. Now, almost all of this is taught in a frequentist, from a frequentist perspective, almost always, and rarely, in my experience, are Bayesian methods even mentioned. Now, if they're mentioned, they're kind of mentioned as a kind of a footnote, or maybe as an extra topic, kind of at the end, like of a textbook. You see an extra, a final chapter on Bayesian methods. So, could ask that, well, what's the reason for that? Why are we using frequentist methods? Why are they the norm, or are they almost exclusively used in teaching, and yet Bayesian methods are increasingly widely used? And by the way, if that reason for their use, that I say computational power, is the reason for their proliferation, then they're just going to get more and more widely used. So it's not going to stop at 20%, arguably. So what I want to do now is just address some possibilities, and these are just kind of thoughts on why Bayesian methods may not be widely used, may not be the norm. Okay, so one is that Bayesian methods and frequentist methods are traditionally presented as mortal enemies. Right, and they fundamentally incompatible with one another. And there's lots of juicy quotes from people backing up this sort of perspective. So like Fisher in his monumental book, Research Methods for Statistical Methods for Research Workers, it began by essentially entirely dismissing Bayesian methods. And so he said, he used the term inverse probability is founded upon an error, must be wholly rejected, and he went on to explain why. And then, like, if you look at some of the big names in Bayesian methods later in the 20th century, you see a similar kind of dogmatic attitude. It's like the only way is to use Bayesian methods. So it seems then like you either use Bayesian methods or you use p-values p-values, etc. And many people are not willing to do that. So many people who may be interested in Bayesian methods are not willing to get rid of p-values entirely. They say, I have to use them. So if the price to pay to use Bayesian methods is to get rid of all these other methods, then I'm not going to do that. Now, my response to that is that there's no reason for this incompatibility. There's no reason why you can't see them as both, as these are two alternative methods, both based on reasonable principles, and so they're not identical, but one is not absurd relative to the other. So it doesn't have to be this kind of fight to the death. So here's another possible reason for Bayesian methods not being the norm, and that's that Bayesian methods have this connotation of of being a subjectivist approach to inference, and this is often how they are presented, at least how they were traditionally presented. And so the idea here is that probabilities, your prior, represents a degree of belief in hypotheses, etc., and then Bayes' theorem, Bayes' rule is used to update those beliefs in the light of new evidence. Now, to put it very simply, and this gets into a very big debate indeed that has gone on really for decades, philosophy really, philosophy of statistics, philosophy of science really. To put it simply, I would say, and others have said as well, that there's ultimately Bayesian methods are no more or no less subjective than frequentist methods. So priors are assumptions. They can and should be based on what we know or what we can reasonably justify. They can be tested, etc. They do not have to represent degrees of belief. Now, interestingly, Andrew Gelman, who's a very well-known Bayesian statistician and has got a very popular blog, he just blogged just about an hour or two ago on this very topic. So if you're interested in learning more about this subjectivist objectivist debate, well, there's a huge literature on it, and go to Andrew Gelman's most recent post to pick it up. But in brief, there's no need to see Bayesian methods in that particular way, I would say. So here's another possible reason. Bayesian methods are regarded as just technically much more difficult than frequentist methods. So if you get an introductory book on statistics on Bayesian methods, you might often see things like what I'm showing on the slides here, and you might think that well, if it's this difficult on chapter 1, how much more difficult is it going to get? Now, this is really an illusion, though, or rather, you can have this level of technical difficulty in frequentist methods as well. So deriving the formulas, for example, for something as simple as a t-test can look as hairy as this. So we don't generally do that. We don't generally expose students in all these different contexts to all these technical details, and so you don't have to do it in a Bayesian way either. So there's nothing more or less technical, I think, about Bayesian methods. Another reason then why Bayesian methods might not have been widely used is this view. Well, as I showed, they're only around 20%. So that means that the 80% is non-Bayesian. So it's a minority approach to statistical modeling. Now, I think the best reply to that is this remark by George Cobb, which was in a different context. So he was talking about p-values and habits and practices around p-values like 0.05, p is less than 0.05 thresholds, and kind of the cult of statistical significance and so on. So this is talked about in this and that special issue on p-values a few years back. I've got the link there. So he was saying that we're talking about p-values. We teach it because we do it, and we do it because we teach it. So there's this circularity between what we do in practice and what we teach, and the same thing applies then with Bayesian methods, right? So if we start teaching Bayesian methods everywhere, people would start using Bayesian methods everywhere, and then you get off that cycle would then take over. So a final point then about why why Bayesian methods might not be used is because they could be seen as just essentially the same thing. So you say, well, Bayesian methods, frequentist methods, are They lead to the same, more or less the same results. And I'm kind of trying to illustrate this here with a linear regression and a Bayesian linear regression. And this here is the linear regression, the frequentist linear regression. And what we've got is the maximum likelihood estimates and the standard error. And we've got the 95% confidence interval. And they're very close to the mean of the posterior distribution, the standard deviation of the posterior distribution, very near the standard error, and the high posterior density interval of the posterior distribution. So they're very similar indeed. So when people see things like this, they say, okay, I'm getting the same results. Practically speaking, I'm getting the same results. And you could get identical results. In fact, I was using default priors here, which we won't get into, but you could get identical results. And people say, well, why would you use Bayesian methods if they just do the same thing? And my answer to that would be, well, for simple, widely used methods, yes, they do often come out to be very similar, if not identical, but not always. And more importantly, for complex models, you may not have a non-Bayesian alternative. So this goes back to one of the original points I was making about, like, Bayesian methods are automatically applicable to any statistical model, where you can define the likelihood function in the prior. Right. So then, kind of finally, and I'm kind of on time, it seems, I just want to wrap up with some maybe personal experience and comments. And so in answer to the question, should we teach Bayesian methods, I would not come down with a hard yes, hard no. I would say it depends. So in some cases, it's a good idea, and in other places, it may not be necessary, may not be worthwhile. So just looking at three examples, personal examples then. So the first is in the core statistics modules taught in a psychology department undergraduate program, where there's approximately 60 hours of contact time spread over 2 years. Here, what we're trying to do is cover that set of topics that I listed earlier on. Things like starting with descriptive statistics, going into inference, and then going regression and ANOVA models, etc. And we just don't have time to. It's hard enough to do all of that, to do that well, so that the students are able to confidently do regression models and ANOVA models and extensions of those in their own research. And we don't have time then to do both, to both Bayesian approach and frequentist approach, and exclusively Bayesian approach just wouldn't fly, primarily kind of for political reasons, but not just really political reasons. Students, if they didn't know anything about p-values, they would have difficulty with the etc. p-values, etc. They would have difficulty with the literature, and even with dealing with their supervisors, etc., who are usually exclusively in that camp. Now, here's another example then. This is an optional module in a psychology BSc degree as well, and like 40 contact hours. And this is an optional module where students choose to do this advanced statistics topic. And there we can teach statistical inference both ways, right? So you start by talking about statistical inference both ways, and then all the examples from then on are using both. And it works very easily. The difficult thing is teaching statistical inference in general both ways. So it's no more difficult to teach Bayesian methods properly than frequentist methods properly. So most people don't understand frequentist methods properly, don't understand exactly what a p-value is. Teaching that properly is a challenge. So it's challenging to teach both of those, but then they can be illustrated easily using in all the applications, generalized linear models, mixed effects models, and so on. And then and so that's an optional module where the students choose it, but then a non-optional module on a data science focused MSc, again, similar approach, and this works very well. So you're starting by explaining statistical inference, and then both ways, the frequentist and the Bayesian way, and then using as you explore all these different models, generalized linear models, et cetera, you can just illustrate them both using tools like as I illustrated there just a few slides back, BRMS and so on. Makes it very easy to do practically. And that's it. I will end there.
Thank you very much, Mark. So can I just remind everyone to post any questions you may have in the Q&A rather than the chat. So we do have one question. I will accept this one from the chat as a first off, but please remember to put it in the Q&A rather than in the chat. So Siri's asking, when would be an ideal time to teach Bayesian statistics to math science undergrads? Is it in the first year, second year, or maybe later on?
Yeah, well, I think it all depends. So I'm thinking in my examples here were psychology students, but when I was thinking about a data science focused master's degree as well, and I would say if you had that type of course at an undergraduate level, then I would say from day one. It could be done at day one. So I think it's really it could be it's all a matter of what you need to teach the students, like what are the learning out, what are the main goals of the course, of the modules, and then I suppose just how much can they take, how technical could it get, and in some cases, depending on the requirements of the course, students will be well able from day one in first year. So I think it all depends. I would not have any general rules here. All depends on the course, the learning objectives, learning outcomes, the students, etc.
Thanks, Mark. And another, I guess, sort of related question is about the politics potentially in trying to introduce this. So pushback from colleagues, etc. So any advice that you might have on that?
Yeah. So I think that again, I would say that this is not really about Bayesian methods at all. It's about change, and I think that's kind of implied by the question as well, that it's just how do you make change possible, big changes, particularly fundamental changes. And so in my department, we switched from SPSS a few years ago to using R, and that was a big political conflict, and so nothing to do with Bayesian versus frequentist, but it was just a big change. So how do you manage it? I've no general rules. I've no general advice. I think that if you can make the case that one thing is just the better way to go, and convince people in the long run that it's the better way to go, and then convince people that the change is, the effort is worth it. Well, I think that's all you can do. That's
fair enough. I don't suppose there's any answer to that, really. Okay, I will take one final question for you before we move on to the next speaker.
Just to say, for this, we are going to leave as much time as possible at the very end of this, after the last speaker, for general questions. So if your question isn't being answered now, we can hopefully return to it.
So have you had any examples of students being confused by the differences between Bayesian and frequentist inference? And how do you deal with that?
Yeah, well, so yes, so so for example, the credible intervals and confidence intervals, that's a good, that was mentioned there in the question, and that's a good example of where people get completely bewildered by the distinction. And so to do that properly, you have to get technical, I think, relatively speaking. That's why I think that the teaching of inference generally is a a relatively difficult topic. To do it properly, to do it in a way that's not misunderstood, is relatively difficult. So that's why I said that it's good. We can teach that at more advanced levels for students, particularly who've chosen the course or chosen a course in data science or something like that. But for students who are well, struggling just to cover those foundational topics, then we just don't really have the time to go into that. So I would say that to be able to to avoid these misunderstandings, which are very easy, then you do have to kind of get into the weeds, and there's no kind of shortcuts here. I think time. You need to spend time, and the students do need to do work as well, as in, you know, readings of good books and so on. So it's there's no easy way, I think.
Okay, thank you very much, Mark.
You're welcome.